Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 1, Lesson 1. Welcome to AP Physics 2. What a thrilling thing it is that you are here in the second year course. So welcome, welcome, welcome. You're amazing. You're brilliant. Thanks for being here. Let us begin. We are in Unit 1, Lesson 1. And Unit 1 of AP Physics 2 is called Fluids, and it is contained completely in Chapter 9. So the unit is one whole chapter long in your textbook. What is a fluid? Sometimes when we're not feeling well, people say, oh, be sure that you're drinking plenty of fluids. Sure, they mean liquids. Fluids, however, in the science sense of the word, refers not just to liquids, but to liquids and gases. Two S's? Liquids and gases. So if it's a liquid, it's a fluid. If it's a gas, it's a fluid. Fluid is a larger category containing liquids and gases. So there we go. We're studying mainly the liquids and the gases. And yet, a lot of what I'm going to talk about today is going to be solids. So we're studying phases of matter or states of matter. Those are kind of synonyms. Phases or states of matter. And of course, when I say those things, you are probably going to think of, oh yeah, solids and liquids and gases. Right. We've got solids and we've got liquids and we've got gases. And I wrote them in that order because solids tend to be the lower energy phase. And then if I add energy to my solid, it might melt and become a liquid. And if I add energy to my liquid, it might vaporize and become a gas. Yes, so these are our three common phases of matter. Yes, if I added even more energy, gases could turn into plasmas. Plasmas are gases that have had so much energy added to them that the electrons just fly off. So we have all these nuclei without their associated electrons. And yes, there are additional, more exotic phases of matter like the Bose-Einstein condensate. But for now, let's just stick with the simple solid, liquid, and gas. And we can change from one phase to the other. And these arrows represent those phase changes. To move from a solid to a liquid, we often want to call that melting. And that is a name of a phase change that makes sense. For some reason, that phase change is also sometimes called or fusion. So if you see fusion used or heat of fusion or something like that, they're talking about what goes on when the solid becomes a liquid. To turn from a liquid to a gas is vaporization. You might have expected me to say boiling or evaporation. Those are two specific kinds of vaporization. But a more general term for a liquid turning into a gas is vaporization. When a gas turns into a liquid, that's called condensation. And when a liquid turns into a solid, we could call that solidification, or we could call that freezing. And so there we go. Now, sometimes you draw a picture and you realize, oh, wait a minute, what if I drew this arrow? I can draw the arrow. I wonder if the thing it represents can happen. So I can draw an arrow going from a solid to a gas. Is it possible for a solid to change phase when energy is added, but not become a liquid, just to immediately turn from a solid to a gas? Wouldn't that be sublime? Yes, it would be sublime. And in fact, it's called sublimation. S-U-B-L-I-M-A-T-I-O-N. And is it possible for a gas to become a solid without being a liquid in between? And again, the answer is yes, that's called deposition. An example of deposition would be frost. There is gaseous water dissolved in the air, and sometimes it gets cold overnight. And if the temperature drops below freezing, and that causes water no longer to be able to be held dissolved in the air, then it turns into frost on your lawn or on your roof or on the windshield of your car. I know that doesn't happen a whole lot in Los Angeles, but it happens in colder places. And then sublimation happens. The example of that is dry ice. We could have solid carbon dioxide. And when we set that out on the table, it does not melt and turn into a liquid. It sublimes and it becomes a gas. And sometimes we use that in the theater department to make smoke. So there's all of that. And just because I like to be sneaky, and I think it's fun when things are challenging, what if I were to write S and liquid, S and L and G for solid and liquid and gas? What if I gave you a quiz and I said, label, and I just had crazy arrows like this. And I just labeled these 1, 2, 3, 4, 5, 6. And I said, okay, label the 6 arrows. Of course you could do that. It might just take a little bit more thought because it's not just about memorizing what word goes where because I rearranged. Anyway, the more evil teachers would quiz you on this way. And you'd say, yay, that looks like fun. I get to think, because thinking is fun. Okay, so that's all I have to say about phase changes among solid and liquid and gas. But that's just a beautiful little representation right there. Solids are known for having what we call a definite shape and shape with an E, and a definite volume. Shape and volume don't change. That's what makes it a solid. Gases are known for having neither a definite shape nor a definite volume. No definite shape and no definite volume. What that means is that the volume of a gas can change. You take a gas and you blow it into a balloon, it takes on the shape of the balloon. If I blow gas into a volleyball and then I blow more gas into the volleyball isn't going to expand once it's full. So I could put more and more and more and more and more gas in the volleyball, but the volume doesn't change. So gases can change both their shape and their volume, whereas we say solids can change neither their shape nor their volume. And then liquid being somewhere in between there, liquids can change their shape, but they do not change their volume. So when I pour a liquid from one container to another, it's going to change its shape. It's going to take the shape of its container, but it's not going to change its volume. The liquid will not expand to fill up the container, but the gas will expand to fill up the container. So liquid, no definite shape, but yes, it has a definite volume. And that's one way of defining solids and liquids and gases. It's one way of understanding solids and liquids and gases. What a beautiful set of notes that is. Hopefully your notes that you're taking right now look similarly beautiful, but I bet you organized it even better than I did. Good for you. You're amazing. Okay. Now, there's that. I've said that today's topic, or this unit's topic, unit 1, is fluids. Fluids are defined as liquids and gases, and yet I'm going to spend the rest of today's video talking about solids. Not only that, but I've told you that solids have a definite shape, and the rest of today's video is about how to change the shape of a solid. You're like, but it's a solid, and by definition as a solid, it doesn't change the shape. Right, but I'm going to talk about changing the shape of the solids. So that's kind of fun. So we are going to talk now about what's called deformation, meaning to change the shape of solids. So most solids to some degree are elastic. So they have an elasticity. When I don't have anything sitting around here that if I had a water glass and I were to smack it, ding, ding, the water glass would make a sound. That water glass is still a solid. It has, a definite shape, but it's deforming and it's vibrating and it's ringing. And there is some elasticity. It can change its shape a little bit, but as soon as it changes its shape, it really wants to go back to its original shape. If you look at this pen cap, I can squish it and I can deform it and make that end there be not a circle, but then it goes back to being a circle again. So there are solids that we can deform a little bit, and then when we let go, they bounce back. And so bounce back, hence elasticity. So we're not talking about permanently changing the shape of the solid. We're talking about temporarily, slightly changing the shape of the solid. And I want to talk about 3 ways that that can happen. And then I want to talk about mathematically how we quantify that shape change. So first of all, if I have something long and thin, like a wire or a rod or a tube or a pipe, if I have something long and thin like this, or like my pen, I can, so it feels like I'm trying really hard to stretch the pen and I'm not. But if this were made of something more elastic, maybe made of metal or made of rubber, like an eraser, I could pull on it this way. And when I pull on it this way, I'm creating what we call tension, like the tension in the rope for all the rope and string problems that we did last year. And so if I were to pull on this, it might get a little bit longer. If I were to squish it this way, it would get a little bit shorter. So the first thing we need to define is, well, what if I pull it this way? It seems like I'm exerting 2 forces there. But you might remember last year that if I pull the rope to the right and I pull the rope to the left, if I pull with 10 newtons and I pull with 10 newtons, we say the tension in the rope is 10 newtons. In fact, if I pull with 10 newtons here and 8 newtons here, that means there's a net force of 2 newtons and the rope's going to accelerate. I don't want that to happen. I want the rope to stay in place. So by definition, the force I exert on this end has to be the same as the force I exert on this end. 10 newtons, 10 newtons. And therefore we say the tension in the rope is also 10 newtons. So don't think about, oh, do I have to add them? 10 plus 10 is 20, or do I have to average them? Or just 10 newtons, 10 newtons, the tension is 10 newtons. So if I exert force that way, and I say that the tension is 10 newtons, that would cause some elongation. If I exerted the forces the other direction, in rather than out, then that would cause some compression. And it might not be surprising to you, more tension would cause more elongation, less tension would cause less elongation. So we need some kind of equation to describe that, don't we? All right, we're going to get to that. There's another way I could deform a solid. And again, we're talking about deformation or elasticity, because once I stop pulling and I let go, it goes back to its original natural length. If I have a block, so I'm drawing this block 2-dimensionally, if I have a block and I exert a force on the top of it, now I'm drawing it 3-dimensionally. If I exert a force here, so it's kind of like if I have my textbook and I'm exerting the force on the top like this, that kind of force. And that force exerted here on the top. I'm not exerting the force at a very specific location. I'm exerting the force on this area. And what that's going to cause is that's going to cause a deformation in the block so that this cross section is no longer a rectangle. The cross section is now a parallelogram. So I start with a rectangle cross section like this. I push on the top surface, and that causes this kind of deformation. That's interesting. So here I have a force that I'm talking about, and I have this cross-sectional area. It turns out that's not so different here, because I'm not only going to talk about the force, the tension that's 10 newtons, but I'm also interested in this cross-sectional area over here that I highlighted. So a thick wire might stretch a different amount from a thin wire. So this area matters. So in both case 1 and in case 2, I'm talking about a force and I'm talking about an area. And it turns out that in case 3, I'm also going to be talking about a force and an area. So in case 3, I'm going to have a 3-dimensional object that might be a cube, or maybe a 3-dimensional object that's a sphere. I have no idea how to make this look 3-dimensional. You know, ooh, look, I'll do shading, except I'm terrible at that anyway. So maybe that looks more like a 3-dimensional ball. And what if I wanted to squish the cube or squish the ball? Well, I would have to push, from all directions, maybe with the air in the room. And so there's all these forces being exerted divided by the surface area. And so in other words, what we're talking about is the pressure in the room. So I've got a force, the total of all these forces divided by the area. And here I'm actually not just going to talk about force and area, but I'm going to divide the force exerted by the area on which the force is exerted. And here as well, I'm going to divide the force, which here, because it's this kind of thing, we're going to call tension. And I'm going to divide it by the cross-sectional area of the string, or the wire, or the tube, or the pipe. So all of these solid deformations, in all of them, to make the deformation happen, I am exerting forces. And I'm looking at how much force, and then there's also an important area. So in all 3 of these situations, force divided by area is going to be called stress. Stress is defined as force divided by area. The area we're talking about, though, is a different area in these 3 different situations. And the way the force is applied is different in all 3 of these situations. Yet, in all 3 situations, we call that quotient, force divided by area, we call it stress. Okie dokie, stress. So this is very important. This is the picture that shows you what's going on. I'm going to move that now. And we're going to talk about the equation. The equation for this is that stress leads to, results in strain. Stress causes strain. Now, you might realize right now already, stress is expressed in newtons per square meter. So the unit for stress is newtons per square meter. The unit for strain is actually, it's dimensionless. Don't worry, there's one more thing that goes here. and that'll take care of the fact that the left side and the right side currently do not have that same unit. So strain is the deformation. Stress is this force that is exerted. It is, we're pushing or pulling, or somehow we are deforming it. How much? Well, how much it ends up moving is strain. How much we're pushing on it is stress. So how are we going to measure strain? Well, obviously, if I exert these two forces, it's going to get longer. So it feels like in number one, strain should be measured in meters, but it's not. Strain for this case number one, strain is the change in length, delta L. So if it gets longer by 0.01 meters, because it got longer by a centimeter, strain would be delta L would be 0.01, but we're going to divide the change in length by the original length, L naught. So my original natural length is L naught. And then I pull it and it stretches by a little bit, that's delta L. So delta L measured in meters divided by L naught measured in meters, the unit for strain is dimensionless. So strain in case one is defined as delta L over L. And it therefore is, strain is dimensionless. Let's go to the ending one here. Strain down here is defined as delta V. It's going to shrink if I push it. If I pull the other direction, it's going to enlarge, but it's delta V over V naught. So the change in volume, again, is going to be measured in cubic meters, but the original volume was measured in cubic meters. So cubic meters over cubic meters, it is still going to be dimensionless. Strain is dimensionless. Isn't that fun? And for number two here, I'm just going to look it up really quick in the book and make sure I'm saying it right. Strain here, it's just not popping into my head. Right. Right, and it is dimensionless. So the strain is defined as how far this has moved. Remember, I started out with a rectangular cross-sectional area, and now I have this parallelogram. That's how I indicate parallelness. With these two single arrows mean these two are parallel. These two double arrows mean these two are parallel. And this distance here, that the corner used to be here, now it's moved over here, delta X. The strain in this case is defined as delta X over this height. Distance X is measured in meters, height is measured in meters, and meters over meters, again, is dimensionless. So in all three of these situations, I've shown you now what the stress is, and I've shown you now what the strain is. Stress always has the unit newtons per square meter. Strain always has the unit, no unit. It's dimensionless. Now, this thing that goes right here is my proportionality constant. It's what makes the units work. So I know my unit is going to be newtons per square meter. And it's a measure of how stiff the object is. So I said, that this pen is pretty darn stiff. It would have a number that indicates that we're not going to have a whole lot of change in length, even though I pull really hard. So I've got a really big stress, right? But it would have a small number here indicating that I'm not going to have a very, we'd have a big number here because we're really stiff. And that way, so if this is, anyway, if this is big, then this is also big, and then this strain would not be very much. So the number that goes here can be found in this table on page 269. So let's see if I can zoom in on that. There we go. And so they're called the elastic modulus, or plural, elastic moduli. This column is for stretching the pen. This column is for shearing the book and turning the rectangle into a parallelogram. And this column is for taking the cube or the ball and just squishing the whole thing and changing the volume. So aluminum is a material, and it has an elastic modulus for changing its shape one way, stretching the rod. It has a different elastic modulus for shearing and turning the rectangle into a parallelogram. And it has yet another modulus for squishing the ball or stretching out the ball. And they have different names, but they all have the units Pascal, which is the same as newtons per square meter. Pascals and newtons per square meter are equivalent units. And it has a different name. It's called Young's modulus. It's called a shear modulus. It's called a bulk modulus. So this number, when I'm talking about here, it's called Young's modulus, shear modulus, bulk modulus. And it's just a number that you look up. And so we'll zoom in here and just look at different numbers. So they're pretty big numbers, 10 to the 10th. Those are really big numbers. Okay, that's all I got. There's this lovely little graph here. And what this is showing is that stress increases, you're pushing harder, strain increases, stress increases, strain increases. This is called the elastic behavior. And then all of a sudden, it doesn't behave linearly anymore. So that's no longer the elastic limit. And then if you stretch something too much out of its original shape, it'll break. And that's sad. We don't want to break things like our water glasses. No, no, no. Okay, so know the difference between stress and strain. Know the units for all those things, especially dimensionless things. I love things that are dimensionless. And these are the elastic moduli, plural, because there are 3 different elastic moduli. Young's modulus is the elastic modulus. There is a shear modulus, and there is a bulk modulus. And I think that is all I have for you today. So thanks for watching the first video of the course. I'm so glad you're here. Have a great day. And remember, don't break the laws of physics.